Yes. Okay. So we have this this transport rays. Okay. And now we know that the transport only occurs along each segment, and we know that the total mass of mu and mu on each segment is the same. Yes. So now we just need to construct. Now you reduce the problem to one-dimensional problem. In one dimension, you have these two measures on the segment, and you need to transport one measure to the other on this segment. And in one dimension, there are just two maps that are continuous. Either you map the median to the median, and you go over all the quantile either in parallel or in opposite way. So this is what you do in each segment, and then you need to show that there is some issues of regularity. So you need to show that if you take the optimal on each segment like this, then the resulting map, say, if you want it to be continuous, things like that. This is very delicate, and there are big. I mean, there is no the map is not regular even in simple cases. If you just take two convex sets, it's not going to be, you have some diffraction points, etc. There are some things in there, but at least to construct a map using this way, you just, on each segment, you do something, whatever you want. So either you take this thing or that thing and take off measurability. That's if you want a map. Okay? But somehow this looks like a bit non-canonical. The map, I think what is canonical is the partition into transport lines. The actual map to me looks less, I don't know. Okay. Okay, if you take the square, it's a completely different theory. Everything changes. Yes. There is the Brenier map. Then first of all, the optimal becomes canonical. It's a gradient of a convex function. It's a completely different theory. And it's particularly nice in Rn. In flat space, the L2 theory is much, much nicer. In Riemann manifolds, I mean, maybe L1 is nicer. But in flat Rn, yeah, L2 is much, much better. Yeah. Okay, so some steps in the proof. First of all, we claim that U is differentiable. Echo? So there's some, that's one, okay. So U is differentiable in any transport ray. So this is why I want it to be often. Why is U differentiable in any transport ray? So suppose that we have some transport ray, you have x naught in the transport ray, and transport ray in direction of theta, that's the direction. Okay, so it means that there is some positive number r, such that this is in the transport ray, and this is in the transport ray. Okay, so the function u here equals, let's assume that u if x0 equals 0, just for convenience. So here u equals 0, here u should equal to r, and here u should equal to minus r. Right, because you know it goes with speed 1 in this direction. So we have these things, okay? And now I claim that I can give you both an upper bound and a lower bound for u of x. Why? So let's do these circles centered at x0 plus r theta, passing through x0 and the other circle. So the claim is that if you look at this circle, inside this circle, I claim that the function u is positive. Why is it positive? Because here it equals plus r, and in this circle it cannot go down by more than r. So it's positive, and here it's negative. And in fact, you can write a better equality. You can write that u of x is always at most, let's say, always at least r minus the distance of x to x0 plus r theta. Right, because here I know that because u of x0 plus this point is r, so we are at least r minus this thing, and we are at most minus r plus x minus x0 minus r theta, right, by triangle inequality. Now the nice thing is that these two functions, they have the same value at x and the same gradient at x, the same value and gradient at x0, right? Because here the gradient of this function is this thing, towards the center of the ball, and here again towards the center, but with a minus sign, so of the same value and the same gradient, and therefore you are sandwiched, you are trapped between, u is trapped between two functions that agree to first order, so u is differentiable at x0. So that's the first step. The second step, questions about this first step? So yes, please.
Where is x exactly located on this?
x0, so take x0 in a transport some transport ray. Any point in any transport, this is x0.
And x without 0 is...
And for any x, yeah, very good. Okay. So I claim that this is true for any x in Rn. I think it's okay. Joseph is okay? Yes? Okay. Now, second fact is that grad u is locally Lipschitz in the union of all, slightly shorten them. Transport rays. And in fact, U is C11. So it means that you can take the restriction of U to this union and extend it to a C1 function all of Rn. Okay, this I will not explain. This is more, I mean, it's a geometric argument, but a bit more delicate than this one. I will skip it. Then the next step is, something with the sound here is different from here, but it's not the microphone. Okay. I do this and I do this. So it's not the speaker at all. I just tend to do this when I go there. Maybe. Interesting. Always you learn something new. Okay, so I will not do the regularity theory, but the thing is that this is enough, C11, this is enough regularity for changing variables. And basically, we want to do something like polar coordinates, some change of variables, so it's good to know that you can do that. Now let me explain how do you change variables. Okay, so this should draw a bit of a picture. So let's take some level set of the function u. So maybe take some, so this is where u equals some number, some constant number, I don't know. Okay, this is the level set, and I call it M, because I think of it as it's a manifold of dimension n-1, maybe not so smooth, but a manifold. And the transport rays, so if there are transport rays, they're here, they are orthogonal. So we know that the gradient is parallel to the transport ray, so transport rays are orthogonal to the level set. Okay, so if there are transport rays, they are orthogonal to the level set. Now I want to take a piece of this, manifold and parameterize it. So let's take some open set, which catches some transport lines. Let's call it, maybe this is U, some open set, some open neighborhood. And in this open neighborhood, I may parameterize my manifold M. So there is some V in Rn minus 1, open, and I have some parameterization. Let's call it phi from V to, this is M, so to this M intersection with U. So this part is parameterized by some open set in Rn minus 1. Okay, so to draw the, okay, so let me write it again. So phi of V is this manifold intersection with U. And so I have this map. I think about it as follows. Okay, now let me draw it again. So this is M, and these are transport lines. And phi is a parameter, they are orthogonal, and phi is a parameterization of M. So now I look at the following map. So I look at f of ty. So y belongs to this V and t is in R. Okay, so I totally gloss over regularity issues, but I look at phi of y plus the gradient of u plus t times the gradient of u at phi of y. Okay, so what do we do here? Let's try to understand. So this is a v in Rn minus 1, okay? And we have our map f to Rn, So what does it do? If t equals 0, so here we have t, and this is y. So this, when t equals 0, this goes to m, as we said, to some part at least of the manifold m locally. Okay? Now, if I look at parallel lines to the x-axis here, where would they go under f? So f takes the y-axis into this manifold m, as I said, the level set of u. And if I vary t, the map is linear in t, and the direction is exactly the normal, the gradient, at least if these are transport rays. So this partition into parallel segments goes to transport rays. Okay, so this is what f does to me. It straightens my partition. It takes this partition to transport rays and make it parallel lines to the x-axis. This is what the function f is doing. Okay, now once you have such a map, okay, you could think about this disaggregation of measure. You can think what would be, which measures here I should put on the needles, so that I would have, if I integrate a function here, I can compose it with f, and first integrate over the needles, and then integrate over the space. And if I have such a map, I can tell you that, at least in the case where lambda is Lebesgue, okay, so that's maybe, and then the next step is that I have this parameterization. In the case where lambda is Lebesgue, the needle density must be what? So I want to have actually a measure here, yes, a measure on this copy of, on this space, on Rn close R, such that under f, the measure here is pushed forward to the Lebesgue measure here. Yes, if I could do that, then I could integrate my function on the needle density on each of these lines. This would correspond to integral over Rn here. So which measure should I put here that will be pushed forward to the Lebesgue measure under f? Well, I should take the determinant. So I should take the determinant of the Jacobian, the determinant of the derivative of this function f. Okay, maybe so let me put absolute value. So this is the needle this will be the needle density on each needle. Let me write it. Well, it's going to be, okay, so T maps to this, will be density on each needle by change of variables formula in the integral. Right? If I have an integral of phi of something, integral of phi of f times this determinant is determinant of fty. This equals the integral of phi on the other Rn under this map. Okay, so this is going to be the density on each needle. This is what it's going to be. Very good. Then you need to understand some things about this. So we have the decomposition. At least I'll argue why we should have some decomposition. And now I need to tell you some properties of this measure, this integration. So first property is that apparently the density never vanishes. Okay, so this, needs to be proven somehow. Because of the fact that needles do not meet, there are disjoint, so if the density would go to 0, okay, you argue why this is never 0. And then you need to look at the determinant itself and understand why this function, for example, is low concave in T. So we need to understand so low concavity in T and this mass balance condition. So let's start with low concavity in T. So we need to look at the differential of this function f and compute its determinant. So what is this determinant? What is this matrix? Okay, so let me write this as a big matrix. So I differentiate, here are the derivatives with respect to t and with respect to y1 up to yn minus 1. And these are the outputs from x1 to xn. So what is the derivative of this function f with respect to t? That's easy. With respect to t, this is the gradient of u. Okay, so that's gradient of u of phi. Okay, and what's the differential with respect to y? So the differential with respect to y, we only see it through phi of y. This function is the composition of x plus t grad u composed with phi of y. So I'm going to have here the differential of phi, okay, which is, I think, n minus 1 by n matrix. And here, times, I'm going to have the differential of the function of the map of this map. Right, so this map, which is identity plus t times the Hessian at phi of y. Okay, so this is the differential, and now my claim is that so the determinant here is going to be some function of y, which I only care about it as a function of t. So it will be some function of y times the determinant of identity plus t plus t. Yeah, I like the t. Times the Hessian of u at the point phi of y. Okay, so this is my claim. Let me see if I can explain it without writing too much on the blackboard. Okay, so I want to understand. So we have a big chunk, which is an n by n matrix here. Now let's pretend that grad u, we choose coordinates, so that grad u is the first unit vector E1. So we can assume that this is 1 and all of these are zeros. Okay. Now the Hessian of u, we know that grad u is parallel. We know that grad u is parallel on this is constant. Grad u is constant on each transport ray. So this means that Hessian of u times grad u is 0 because the differential of u in this direction is 0. So it means that this would be a matrix. This is symmetric matrix. So if this is 1, this matrix would be like with zeros on the first matrix of this form. And therefore, and then, okay, so I mean, so that, so therefore, when you therefore, when you compute this determinant, you have 1 times this big minor here, and this big minor here will be all the, I mean, it would be everything in the matrix Hessian times some matrix depending on y. So what you would get is this the identity plus t times this Hessian. Okay, I hope. I mean, maybe you want to do it yourself, but let me claim that this is okay. Yes. Now, so this is anyway. So this is the Dindel density, determinant of identity plus t times this matrix. And now low concavity is an easy thing. Why is low concavity an easy thing? This is a symmetric matrix. Okay, and we need to understand the low concavity. Should I explain a bit better why the determinant of that matrix was what I claimed it is? Maybe it was too it was sloppy. So I claim that if I have a matrix of this form, so it was 1, 0, 0, 0, and then here I'm going to have identity plus t sum of A times some another matrix B, and A was a matrix like this, with some A prime. I claim that this is the same as determinant of A plus TA prime, which is the same of A, which is the same as the determinant of I plus TA, because we only get something here. This is what I claimed. Yeah, times some function of, well, some function of B, which is non-zero, times this thing. So yeah. Am I convinced myself? Who knows linear algebra in this room? So this is n minus 1 times n, and this is n by n. So
you expand with just the first column, right?
you expand by the first column, yeah. So here I know that it's, but here's, okay, so you don't care about, right, you expand the first column, right, yeah, that's it. You expand the first column, you get this little matrix, and the determinant, that's it. Very good, thank you, Stashek, yes. Yeah, so it is just, right, so it is just the determinant, yeah, it is exactly the determinant of this little matrix times the determinant of the block. So you don't care about the first line of B, you just care, yeah, times the determinant of B prime, where B is something, and B prime, which is n minus 1 minus 1. Yeah, very easy, yes. Thank you. Okay, now, very good. Now we have this formula, and now we need to, so this is, so let me recall, the Needle density. The Needle density is T on times the determinant. So on each needle, T times some function of Y, this determinant. Okay, so this is, as a function of T, this is a fixed symmetric matrix. And we know that the density does not vanish, that's important. The claim is that such function is always low concave. So this is the characteristic polynomial of a symmetric matrix. Okay, symmetric matrix has only real eigenvalues, so this is the product of T minus lambda I. Let me put absolute value everywhere. Okay, so this is what we have. We have n minus 1 eigenvalues, and this is this density is a function of T, where these are some eigenvalues. And since this function that never vanish, so what do I have? On some interval, I know that these functions don't vanish. So lambda is outside the interval on which the transporter is defined. But this function, T minus lambda, is low concave on each interval where it does not vanish. Right? So therefore, it's a product of low concave function. So let me write it. Okay, so it's a product. So the Needle density is a product of n minus 1 linear terms that do not vanish, of n minus 1 linear functions that don't vanish, and we had this profound observation from the polar coordinates case that the linear function is low concave. So this is low concave on 0 infinity, and the product of low concave measures is low concave. Okay, so the product in itself, it is low concave. So the Needle density is low concave. Very good. And next, what remains to be explained is the mass balance condition So we need to show that for almost any I, we want to show that the integral of f d mu I is 0. Yes. Okay. Now we have, now we recall that mu, so the integral of u d mu is the supremum over the maximum. It's attained. It's the maximum over all one-Lipschitz functions of the integral of v d mu. Okay. And we have this, we already have this integration of measures, so we can write this integral, this step of the proof, as the integral over the space of segments times the integral of u d mu I d nu I. Okay? And now the idea is that, is the following. Now I don't talk, I'm still. Okay, so the idea now is that if the integral on some needed is non-zero, then okay, so let me just write down what we know from the top board. So what we know, so we know that the integral of u times f d lambda is the maximum of the integral of v times f d lambda over all one-Lipschitz functions v, okay? Now the question is, what kind of variations can we do to one-Lipschitz function? And it turns out that if you're on a transport line, it is possible, so we can add a value, a small number, could add a constant to an Lipschitz function in transport ray, and modify it a bit in a neighborhood of transport ray in the immediate neighborhood by keeping it one Lipschitz. So basically, so what type of variation? So I want to understand from the optimality conditions that the integral of f on each has to equal to 0. So basically, what kind of variations, infinitesimal variations of u are allowed? You cannot change the value of u at a single point on a transport line because you know that it's strained, it's completely trapped between, it has to go in speed 1. So if you change it, there is no other way to change it while keeping it a Lipschitz function on the transport line, right? Because here it goes with speed 1. Any change in a single value would destroy the one Lipschitzness. However, you can add a constant to the entire transport line somehow, and making the change, and also need to adjust the function maybe in some small neighborhood here. But basically, that's the freedom that you have. You can add a constant to u on each transport line, and by this maximality condition, this implies that for almost that the integral of f d mu I has to be 0, because if it was not 0, for almost every. Because if it was not 0, you could add a constant and increase this maximum. So at least this is the intuition why it has to be the case that the integral of f on each transport line has to be 0. Okay, so this is all I want to say about the proof of this linear composition theorem. Do you have any questions? Wow, many. Yes, please.
So if you do a slicing decomposition, you can also prove some.
What is slicing decomposition?
Where
Parallel? But the segments are parallel?
No, not where the segments are parallel, but you start with some convex region containing your support, and then you iteratively bisect it using hyperplanes zero mass condition.
Yes.
You end up with a bunch of needles at the end.
Yes.
That should satisfy all the conditions you wrote in the theorem.
Almost all. Satisfies some of the conditions. But for example, we see some. So this is the Gromov and Millman and Payne-Weinberger and Lovasz and Simonovits localization. And some of the applications you can prove during that method. But here we have another power, which is this one-Lipschitz function. And we're going to use it to prove something else. Yes. More questions?
Well, the heuristics, I would say, am I correct that the mean zero is just mass preservation, right?
Yes, but why is it reproduced on each?
So since you are heuristic, is that since you are transporting on the ray,
It must be. It must be. Right. Actually, you can. Yeah, actually, yes. You don't have. Right. Yes, you're right. You can use the gamma. You can use the Fakstev gamma. It must be just by this. Yes, yes. Right. Yeah, I just wanted to prove it as a theorem on U, on the Lipschitz function. But you're right. If you have the gamma, yes, it's a better argument than this. Yeah, thanks. Okay.
Just a technical question. In the first step for this mass balance explanation, so we can use this disintegration of measure. It's just the upper approach. On the right.
Here?
You should recall something to inequalities.
Yeah. So you was the optimizer of some optimization. You came from some optimization problem. Yeah, d mu is f. Okay, very good. So this is d mu. Yeah. So I wrote it twice. So f d lambda is d mu. So I wrote it in two possible ways. F. So the measure mu is mu 2 minus mu 1. Okay, and f was the d mu to d lambda, which is for lambda. Oh wow, no, for lambda. Let me do it here. I just did it for everything. I work with the reference measure lambda, with the Lebesgue measure all the time. So let me write again. So this is the integral of uf d mu I d nu. Oh yeah, d nu. Yeah. In the maybe did I write in the theorem? Where is the theorem? In the theorem I want. This is the disintegration. Maybe I did not write it properly in the theorem. Maybe I switched here. I don't remember. But that's the disintegration. Maybe I wrote here a mu. Could be.
Yeah, so you use it for u.
No. I want lambda. So if for u, there should be lambda here. This is the disintegration. Sorry for this typo. And indeed, as Staszek said, this the last step you could do it just by using gamma. It's a better idea. Yes, please, Beatrice. No, what I say is that we already proved that we know that we have this gamma, this coupling gamma, and we know that transport happens only along transport trays. So there must be some balance, otherwise there is no transport. If there is transport between two measures, then they have the same total mass. And since it happens along each transport ray separately, you could argue that on, I mean, it's not like 1 second, but yeah, you can argue that on bunches of transport trays, the total mass should be 0, and then by passing to the limit on each transport tray, the mass must be 0. That's the... More questions? It's a measure space. It's a measure space. There is a measure on it. There is some sigma algebra of measurable sets. And it's, the measure is good enough so that I can have this disaggregation of measures. So I can just measure space. More questions? Yeah, this was a bit tough. Yes, Beatrice.
How do you find the commutation? Is it, in concrete examples, is it easy?
If you have symmetry, it's easy. Like, I don't know. If you want to transport, suppose you have some axis of symmetry, I don't know, you have some shape like that, and I want to transport the measure with this distance, this half to this half. Okay? So, yeah, it's going to be this. This is the optimal one. And for L2, you don't know it. I mean, for L2 optimal transport, it's hard to say exactly what happens. But here, yes, this would be, how would you, yeah, so if you have symmetry, you can find it. In general, how would you, yeah. Okay, so let's see 2 applications. More questions? Can I ask more are coming? Yes, please.
So about the idea that transport happens along rays. So if you have a transport map, does the image of a ray contain is the ray itself, or is it if there is a transport map and you take a ray, you take the image of the ray, but
Yeah, it's the same. Yeah, yeah, yeah. T of the ray, yeah, the ray is invariant under T. Yes, exactly. For the optimal, for any a optimal map, it's not the. But yeah, for optimal map, it must keep the ray. Yes, yes. Due to gamma. The one-Lipschitz function is the dual object to the coupling gamma. So these are two dual objects. It lives in a dual space. If you look at the Banach space of one-Lipschitz functions, its dual is the space of measures. So it's called the Kantorovich-Rubinstein space. So that's functional dual. Okay. Yes. So yeah, I can erase this, and let's have two applications. So one which is general for convex localization, the other which uses this one Lipschitz function. So proposition, reverse Helder inequality for polynomials. Which is due to Bourgain in 91. So let X be a local random vector in Rn. P a polynomial of degree at most D. P, H, because P will be LP. H a polynomial of degree at most D. Then for any P and Q, I want to include 0. So in general, we know that the LQ norm of H, it should be at least the LP norm of H. It's a norm only if it's above 1, but I use the word LP norm, the LP quasi-norm, also for P which is above 0. So in general, the Q norm should be larger than the P norm, but the claim is that you can have a reverse inequality where the constant here depends only on the degree D, not the dimension, the degree D, and Q, no depends on P because I can put 0. Okay, where CDQ depends only on the degree and on D and Q. Okay, how do we prove this theorem? So linear decompositions allow us to reduce n-dimensional problems to one-dimensional problems. That's the use of this theorem. So let's first prove it in one dimension. So in one dimension, there is a... No, because I can take P equals 0. Yeah, that's the... Yeah. Okay, so let's prove it. Okay, so in one dimension, so this is an argument, a very elegant argument by Bobkov. So how do I do it? So let's assume H is monic. Why not? So H of T is the product of D, most D, T minus lambda I, for some lambda I complex numbers. Okay, and therefore the LQ norm of H in one dimension. So it's the LQ norm of this product. And by Helder, it's the product of slightly bigger norms. So since we have D terms, it should be D times Q. Okay. Now this is low concave, one-dimensional low concave. And we know that one-dimensional low concave random variables satisfy reverse order inequalities, right? Just the linear function itself satisfies reverse order inequality. And here we have x minus some complex number, and this is just a constant which does not interfere at all. And therefore, by what we proved, so by reverse Helder from yesterday, reverse Helder for linear functions of a local random vector, we know that here we can have, we can replace it by the p norm, by the zero norm even, we can do it. And what we pay is a constant times dq, or say q plus 1 or something, times the L0 norm. That's what we proved yesterday. And this equals, so a constant q plus 1 to the d times. Now, the nice thing about the zero norm is that it's multiplicative. So here I can put back the product inside the L0 norm, which brings me back h of x. So this is in one dimension. Now, for n dimensions, now in n dimensions, what do? So we're given our function f. Let's denote by maybe e would be its LP norm. Okay, so let's denote f of x to be h of x to the p minus e to the p, so that the integral of f d mu is 0. X is the square according to the measure mu. So integral of x d mu is 0. Now, mu is log concave. Apply needle decomposition. So we know that mu would be the average of some measures, which are, again, log concave. And we know that this is log concave. And we know that the integral of f d mu I is 0. Integral of f d mu I is 0 means that the integral of h to the p d mu I is again e to the p. Okay, so on mu I we have the same LP norm, and therefore by the one-dimensional case we have okay, so by the one-dimensional case, we know that the L Q norm on mu I of H is at most some CQD times the LP norm of H on mu I because it's log concave. Okay, which is, I think, E. Right, because, yeah. So hence, the LQ norm of H with respect to d mu, okay, on Rn, it's the integral on each needle separately of H to the Q d mu I, each of them, well, by the way, in this decomposition, okay, I may assume all are probability measures. That's important, actually. So mu was a probability measure, and in the composition, if it was the probability measure, then I can multiply it by some constant and move the mass to nu. I can define nu tilde, which is, I can move mass from u to actually it also appears in the notes this way. And this is at most CQD to the power q, times the function e to the q. Okay, or if you want, this means that HLQ of mu is at most CQD times E, or CQD times LP. Okay, so this is this application, it does not use the full force of optimal transport, and I think tomorrow we start with some application which does use more information from the optimal transport, this one-piece function U. Okay, so this is all for today for me. And 1:45 is Joseph.